All right, subscribers, welcome back to another episode of Science with Surback. Today, what we start into is organic chemistry. And organic chemistry is just another type of chemistry that's going to deal specifically with some compounds that are deemed organic. And we'll get into what that means here in a second. Now, before we get into section one here, what I want you to be able to accomplish by the end of these lessons is these three objectives. Number one, describe the structures of alkenes. Objective number two, name an alkene by examining its structure. And objective number three, draw the structure of an alkene given its name. So we start out here with what is organic chemistry by outlining this term of organic compounds. Now, organic compounds is just a term applied to all carbon-containing compounds with a primary exception that we'll get into here in a second. So that primary exception is going to be compounds that are considered inorganic. So they have carbon with them, but there are some few exceptions. And some of these examples include things like carbon oxides, carbides, and carbonates. Now, just as a reminder, remember a substance like a carbonate here, that's a polyatomic ion that we've discussed before. And our carbonate, remember, has this formula of CO3, and it's polyatomic ion, so it has that 2- charge. So again, it has carbon, but because it's combined in this way, it's considered inorganic. So big thing here is to remember carbon. And now how organic chemistry really got its start was early in the 1800s, more to the mid 1800s. They couldn't synthesize organic compounds in the lab. Well, eventually through a method, they were actually able to produce organic compounds in the lab, and then once they were able to synthetically produce it, then they could get started with actual research and actual in-depth analysis of this stuff. So it actually hasn't been all that long ago that we've started organic chemistry or really gotten into the details of organic chemistry. Anyways, we get into the importance of carbon. The key word here, and if you want to underline it here, it's not a bad idea, it is carbon. So why do we have carbon? Well, number one, carbon has 4 valence electrons. So with 4 valence electrons, what carbon can do is it can form 4 covalent bonds with other elements. Now, usually in organic chemistry, those 4 other covalent bonds are either going to be a carbon bonding to another carbon, or they're going to be a carbon bonding to another hydrogen. Now, our organic molecules aren't forced to bond with another carbon or another hydrogen. They can actually form a bond between elements relatively close to carbon on the periodic table. And some of these examples include nitrogen, oxygen, sulfur, phosphorus, and other halogens on the periodic table. So almost any other nonmetal that carbon can bond to in an organic structure. Now, I want to talk one point here. If we form a covalent bond, a carbon forms a covalent bond with another carbon, well, now there's an additional spot for this 4 covalent bonds. Yeah, one of them's occupied by attaching a carbon to a carbon, but now we can expand another carbon and attach a carbon onto that carbon, and then another carbon could get attached onto it, and so on and so forth. And so what happens here is that organic chemistry sometimes, I wouldn't say it has a negative annotation, but has a difficulty because there's so much to think about. So my final point here on this page is this. Because a carbon can bond to another carbon, they can form things that have carbon chains that consist of 2 to thousands of carbons bonded together. They can form complex branched structures. They can form ring structures. They can form things that look like cages, like Buckminster flooring. If you Google that, it almost looks like a soccer ball, but it's all connected together with roughly 60 carbons there. And so these organic compounds can get relatively complex relatively quickly. So there is that final point here. I know it's kind of squished in here, but it says carbon bonding to other carbon results in lengthy carbon change, branch chain carbons, ring structure carbons, and then these cage-like structures. So again, I think some people associate the difficulty with organic chemistry with the great vast amount of molecules that can be formed from organic chemistry. What we do, we concentrate here on the basics first in this particular chapter. So what we are going to be looking at is going to be hydrocarbons. Now, hydrocarbons are a specific type of organic compound, and hydrocarbons are only going to be the simplest organic compound that consists of only the elements carbon and hydrogen. Now, remember, a carbon can bond to another carbon, and that carbon can bond to another carbon, and that can bond to another carbon, and so on and so forth. So what we end up having with our hydrocarbons is thousands, literally thousands upon thousands of different hydrocarbons that can exist. Now, since there's so many different hydrocarbons, we have to have a way to separate or classify these hydrocarbons into different categories. So we start out here with our category called an alkane. Now, an alkane is just simply defined as a hydrocarbon that only has single bonds between atoms. So another important thing with our alkanes is that they are going to have a specific ending on their name, and this is going to be an ANE ending. Now, this chart below here is really important. And the importance of this, and I should have labeled this is the names of alkanes. And now, it's really important to utilize this chart, not only for this section, but throughout this chapter on hydrocarbons. What happens here is this. The name of an alkane is determined by the number of carbons that it has. So if a hydrocarbon only has one carbon, and again, it's based on the number of carbons. If it only has one carbon, then it is given the name of methane. And if it has two carbons, it is given the name of ethane. Again, the key thing here, all of these have an ANE ending, and that will be true all the way down this chart for this process. Now, something with 3 carbons is going to have the name of propane. Something with 4 carbons is going to have the name of butane. Something with 5 carbons is going to have the name of pentane. Something with 6 carbons is going to have the name hexane. 7 carbons is going to have the name of heptane. 8 carbons is going to be the name of octane. 9 carbons, a little bit different here, is going to be nonane. And then something with 10 carbons is going to have the name of our alkane given as our decane. Now, this is really important because, yes, we're just talking about alkanes, and yes, we are just talking about hydrocarbons that have a single bond, but this will be our chart that will actually refer to relatively throughout this entire chapter on organic chemistry. So it's really handy to look over this chart and keep this chart really handy, because when we get into naming, this will be utilized throughout that naming portion. All right, so now what we are going to shift gears to is how do we draw this, and how do we show that we have an organic compound, and how do we show that we have a hydrocarbon? So if we just change the page here, so it's really important to understand how to represent or how to show these alkane structures. And we have 3 different ways that we will show this particular way to represent an alkane. And so we start out here with a molecular formula. Now, a molecular formula represents the specific number of atoms of each element in one molecule. So really what a molecular formula is, or what it looks like, is just a standard chemical formula that we've been dealing with throughout chemistry here. So a good example of this is going to be in our sample ethane, or our alkane ethane. So if we have ethane, remember ethane means 2 carbons. The way we represent the molecular formula of ethane is just going to be C2H4. And so with that, with ethane in mind, we have here, whoop, I made a mistake here, C2H6. That's my mistake there. C2H6. I knew something looked weird. But that is our formula for ethane, and that's the molecular formula. Now, in organic chemistry, it's a lot more helpful to see these stretched out structures, and so that's what these 2 things on the bottom do in detail here. So these are more, in my opinion, more organic oriented because they show the actual structure. So the condensed structural formula is going to be a way in which we represent the formula by saving space of the organic structures by not showing how the hydrogen atoms are branched off the atoms. So again, to show this, we're going to stick with the same example, ethane. In that molecular formula, it looked like the formula we'd just written down the entire year. In our condensed structural formula, if we stick with this same example of ethane, we have this. We need to show that our carbons are bonded together. So how we do this is by bonding the carbons together in a single covalent bond, because that is our alkane. And then we attach right next to these carbons our hydrogens. And now each of the carbons has 3 hydrogens attached to it. That's where we get the total of 6. 3 plus 3 is that total of 6. Now, notice here, I like to have the carbons bonded. It is not wrong if you write CH3, connect it with one line, and write CH3. There's multiple versions, and we'll go over those in our example. We'll see those, but just know in this condensed structural formula, what we are doing is we are representing that the carbons are bonded together. The hydrogens are always going to be attached to that particular carbon. And again, that will be shown in our example. Now, if we move down to our structural formula, This right here, it's going to be another way to represent an organic molecule by showing specifically how the hydrogen atoms branch off of the carbon atoms in organic molecules. So again, we stick with our same example here of ethane, and this time we're just going to show that yes, the carbons are attached to hydrogens in a specific format. So again, we stick with our same example of ethane, which is what we've been doing this entire page here. And so in ethane, if we drew out the structural formula, we have our carbon attached to another carbon, and then on this first carbon here on the left, there are 3 hydrogens. In a structural formula, we show the covalent bonds that connect the carbon and hydrogen together. And we do the same thing for this carbon here on the right. The problem with this, it's really nice because it shows you specifically how our hydrogen is attached to our carbons, but the problem you can see is that this takes up a large chunk of room. So the majority of the time what we're going to be doing is this condensed structural formula. And there's a couple different formats that we'll go over as we get more and more into organic chemistry. Now what we need to talk about before we really get into naming and drawing organic structures is some basic terms, some basic concepts of our particular organic compounds. So we start out here with this term called a homologous series. Now, a homologous series is defined as a series of compounds that differ from one another by a repeating unit. So to put it simply, it's a fixed numerical relationship that exists among the number of atoms in an organic molecule. So it's a lot easier to show this in alkanes, where we're starting to become familiar with the formulas associated with this. And so in our alkanes, they have a specific mathematical formula that expresses this homologous series. And that mathematical formula is as follows. Now our C represents our carbon, our N is going to represent how many carbon atoms, and then we have a formula for the amount of H's. We have 2 times N, the number of carbons, plus 2. So again, our N is going to be our number of carbons in our atoms. And I'm going to put this in our alkane because we're dealing with a single carbon-to-carbon bonded molecule, organic molecule here. The formula will change for when we alter the single bond between carbons and carbons. Now, this formula can be used to determine any molecular formula for an alkane. So an example of this is when we have something like heptane. If we want to know, well, what is the molecular formula for heptane, we can utilize this particular formula. Now for this example, heptane, if you look back on that chart that we completed earlier in these notes, heptane is going to have 7 carbons. So we can insert that number 7 into our formula. So all I'm going to do here first is I'm going to put C7, that's N is replaced by the number of carbons, and then our H is 2 times 7 plus 2. So 2 times 7 is 14, plus another 2 hydrogens is 16. So the formula for heptane becomes C7H16, and that would be our molecular formula for heptane. Now what we can do here, before we get into naming, there's one more thing that we need to talk about. And that's a little bit more along the lines of how we represent or how we draw some structures, but it gets into some details with our alkanes. So far, what we have discussed when we did that chart or we named that chart was a concept known as a straight chain alkane. Now, I didn't give you that name, but specifically here, our straight chain alkanes are the organic compounds that are bonded to each other in a single line. So any one of those hydrocarbons that we went over, or alkanes that we went over in that chart of 10, is considered a straight chain alkane. So one of those examples there is propane. Now, propane has three carbons bonded to it, and if we were to draw out that condensed structural formula, it would look like this. Now, one thing I'm going to do here is this. I'm going to make all the hydrocarbons look the same. So just know here that this bond that I draw is actually connecting our carbons together. It's not connecting a hydrogen to a carbon, it's connecting a carbon to a carbon, and this middle carbon is connected to our other middle carbon. Now, I made a mistake here and I put a 3 originally, but remember, carbon can only have 4 covalent bonds. So that's why I reduced the number of hydrogens down to 2 when I erased that value there. Now, we move on to something that brings a little bit more complexity to our alkanes, and this is something known as branch chain alkanes. And so what happens here, simply put, branch chain alkanes is carbons that are connected together, alkanes, that are not in a straight line. So this factors into carbons' ability to connect to potentially 4 other carbons, and it makes these branches. Now, these branches will determine how the structure and the properties of a specific alkene, what those properties are. So the best way to see the difference between branch-chained and straight-chained alkanes is through an example. And so in my example, what I'm going to do here, I'm going to give myself some space. I'm going to draw out this compound called 2-methyl propane versus our structure, a straight chain structure of butane. Now, to save some room here, 2-methyl propane. What it is going to look like is this. It is going to have a CH3 group right there connected together. This is only going to be a CH, and I'll tell you here in a second, connected at the end to a CH3 group. Then at the top, this is where that 2-methyl, which we'll learn here in a second how to name that, but we have this particular structure pertaining to 2-methyl propane. And I'm going to draw an arrow so we have that. Now, butane on the other chain, straight chain, is going to be a straight chain hydrocarbon. That's going to have 4 hydrocarbons connected together. And it is going to look like this. Now, if you count this, and you can count these, we are going to have the same formula. Both 2-methyl propane, the molecular formula for 2-methyl propane is going to be C4H10, and the formula for butane is going to be C4H10. Now, you can tell just by looking at how I drew these are 2 different structures. And this one over here is a branch chain, and it affects some structures. So let's get into the details of how specifically can I go from this name to drawing, or vice versa. How can I go from this structure to a name? So what we do, we have this protocol that is outlined by the International Union of Pure and Applied Chemistry, and what they do here is they develop naming methods. They're actually the organization responsible for naming new elements on the periodic table and confirming that they are actual elements. And so they determine these steps. And another reason they determine it is that we have scientists all over the world that are naming the same structure. So if you call it in one place something, and somebody across the world calls the same molecule something else, we have confusion. So we have to have a way to eliminate that confusion. So the first step to name a branch chain alkane is, number one, count the number of carbon atoms to its longest continuous chain. So I'll show you how to do this, but we're going to count the number of longest continuous chain carbons. Then that chart that we filled out, you need to take the number of carbons and correlate it to that name in that chart. Now the second step is to number each carbon in that parent chain, or the longest chain. So when we number it, we have to number it in a specific way, and that's so those branches that we talked about just previous get the lowest possible number. And the best way to do that is through an example. Our third step is name each attached group, or name each of the branches. Now, if we run into an alkane, a branch chain alkane that has multiple of these same branches, what we are going to do is we are going to use prefixes, similar to how we named our covalent compounds. If there were two of the same atoms, we called it a di, or put the prefix di. We put the prefix tri for 3, and so on and so forth. And those prefixes can be found in that handy dandy periodic table packet that you have. Now, when we have multiple branches that aren't the same name, we have to place those in alphabetical order. But we don't, in that alphabetical order, we don't consider the prefixes. So an example of that, if we have a branch that is an ethane branch, and we have a methane branch, the ethane, because it starts with an E, is actually going to be in front. Now, one thing that we have to do here is we have to write the entire name, the final step, write the entire name using hyphens to separate numbers from words, and commas to separate numbers. So that last step here, you basically smush everything that you've compiled together into one single continuous flowing word. Now, one thing that I failed to mention that is really important, up here when we talk about the branches, we will place the name that we use from the chart, except one major exception, and I would star this, highlight it. The A and E ending is changed to YL. Okay, so that is really important here, that it is going to change not to A and E. We're going to chop that off, and we're going to put YL to represent that it is a branch. And now these branches are called substituent groups, and it's because you could switch out what is attached on that particular branch. Now, I know these steps are quite lengthy, and I want you to utilize this to your reference as you go through this process. But the first thing that we are going to do is we're going to find the longest chain carbon. That's step one up here, and it's probably the most important. So we start out with this example with identify and name the longest chain carbon in these organic molecules. So a longest continuous chain, how I like to envision this is I like to think of this as connect the dots. Now, our dots in this case are the carbons. And if I connect the dots, I place my pencil down and I can only go through each dot or each carbon once, and I cannot go backwards, okay? So there is no going backwards in this process. And what you try to do is you get the longest flowing chain carbon in this particular structure. Now, what I always do first is I usually try to list out the longest chain carbon from left to right. It's not always the case, but from left to right, again, if I pick up my pencil, I have to stop. So I'm going to continue that flowing chain or that longest chain carbon. So across the front, I have 1, 2, 3, 4, 5, 6, 7, 8. Now, the whole goal is to find the longest chain carbon. So what I am going to do is I am going to flow up and to the right, and then I'm going to go up. And remember, I already have 8 carbons, so the goal is to be 8 carbons. So I have 1, 2, 3, 4, 5, 6, 7, 8. Again, 8 is the same number that I counted across, so that's not longer. Now I'm going to go up and all the way to the right. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so again, double check to see if I can get any longer carbon. Remember, it's like connect the dots. You can't go backwards. And once you pick up the pencil, you have to stop. So anywhere on here, I'm going to double check myself real quick, but nowhere here that I see anywhere that I can get more than 9 carbons. So our longest carbon chain, our longest carbon chain, or our parent chain, if you want to go via the directions given here, was 9. Now, 9 doesn't really help us besides it references our chart. So if you look back at the chart we filled out on page 2 and you go to 9, the name for that longest chain carbon is going to be nonane. So the name here, yes, 9's important, but the name becomes nonane. And that would be placed at the end of our name, and we'll see that here in a second. Now this one, a little bit more difficult here because we are going to have some ups and downs. And initially here, I always like to start counting straight across because that's most of the time the name there. And so we have 1, 2, 3, 4, 5, 6 carbons. Again, the goal is to beat 6 carbons. You have to continuously flow your pencil. You can't pick it up. The moment you do, you have to stop counting, and you cannot go backwards, only through each carbon once. So I see this big horseshoe as a potential for a lot of carbons. So if I start over here, I have 1, 2, 3, 4, 5, 6, 7, 8. The goal is now to be 8. That is the longest chain carbon. And so I'm going to try a variety of ways to beat 8. I have 1, 2, 3, 4, 5, 6, 7. Nope, did not beat 8. I'm going to go over into the bottom here. 1, 2, 3, 4, 5, 6, 7. Nope, not bigger than 8. Up and over to the right here. So 1, 2, 3, 4, 5, 6, 7. Still not 8. And I'm going to double check real quick. There is nothing bigger on this particular alkane that has greater than 8 carbons. So right here, our longest carbon chain becomes 8. So what we do here is we look back on our chart, and for something with 8 carbons, that name is given as octane. So our parent chain, our longest chain carbon, would be given the name of octane. And now that would be placed at the very end of the name, but this is most vital. Find that longest chain carbon, and sometimes it's just a guess and check method. So let's go in here and let's try to name a couple examples. We start out here with the structural formula for this organic molecule. Now, again, the structural formula is going to show how the carbons are attached to the hydrogens. When we do this first step and we find the longest chain carbon, we are going to just want the carbons connected together. So don't get your mind confused about the hydrogens. They're there because we're dealing with a hydrocarbon. They're part of that molecular formula, and we have to factor those in. But when we're naming organic compounds, we are just concentrating on these carbons. So our carbons here, again, I always like to go straight across because sometimes that's the simplest and longest chain here. And so if I do that, I'm just counting the carbons. I have carbon 1, 2, and 3. The goal is to beat 3 carbons. So I have carbons 1, 2, 3, still not bigger than 3. The only other option I have is carbons 1, 2, 3, still not bigger than our longest chain carbon. So our longest chain carbon here, we have 1, 2, 3 again. So the first step is to identify the longest chain carbon. And I just established that this longest chain carbon was a carbon of 3. And so again, if we reference this chart, we look here. The name for something, an alkane that is with 3 carbons, is propane. So I end up writing down propane, and I'm going to come back to this here in a little bit. Now, the carbons, the next step was to number them. And we have to number them so that the branch is given the lowest possible number. Now, we only have 2 ways we can number this particular chain. We can either go from left to right or right to left. The whole goal is to get this branch with the lowest possible number. So we can number it as 1, 2, 3. At that point, the branch occurred at carbon number 2. So our whole goal is to number it so this gets the lowest possible number. If we go backwards, we get carbons 1, 2, 3. Again, this has a branch. This branch branches off at carbon 2 no matter how we number it. So a key thing here, I like to actually number, especially as we get into a little bit more complicated of molecules, and I am just going to number it. In this case, carbons 1, 2, and 3. So what I do from here, I like to dissect my organic molecule as I name it. And this guy right here that I'm going to box in here with this purple pen, this guy right here is our branch. And so what we do with our branches, in this case we only have one, what we do here with our branch is this. We first identify what carbon number does this branch occur at. And so it branches off the carbon number 2 of the longest chain carbon. And so it's important here, again, when we talk about what carbon it branches off of, we're talking about that parent chain. So what we do here is this. At carbon number 2, what we have is this. We have an attached CH3 group. Now we ask ourselves this. Okay, something with one carbon is going to have a specific name. So if we look at our chart, the name for something with one carbon is methane. And so what I do here is I write down the name methane. Now, that rule that I added on at the very end of the steps said, hey, if it's a branch, I can't have this A and E ending. I have to change it to a YL ending. This YL ending indicates that this attached group is a branch and not part of that parent chain. Now, the last step here is always double check to make sure you've accounted for all the branches. This is a pretty simple organic molecule, and we have accounted for all the branches. Now, when we go to name this structure, we always start out with our branches. Now, it says name the branches in the simplest or alphabetical order, but because we only have one, we just start out with that particular branch. Now, how we name it is we start out with what carbon number is our branch at. So we start out with a 2, and then we put the changed name of that branch. So we put 2-methyl, and then smushed right into it. Because we've named all the branches, what we do here is we tack on the longest chain carbon name right to the end of this particular name of our branch. And so for this organic compound up here, if we name it via the IUPAC, or the International Union of Pure and Applied Chemistry, the name becomes 2-methylpropane. And if you Google this, 2-methylpropane, and make sure you're specific here, 2-methylpropane structural formula, you will get an image that looks exactly like this image here. So it's nice with Google, you can check yourself as you go through this process. Now, moving on to something that is a little bit more complicated. With this here, there's a little bit more complicated, is this. We have an alkane, which is obviously a lot more complicated because there's a lot more going on. But our steps are going to stay relatively the same. We're just going to have to do some added things because it's a bigger alkane, a bigger molecule that we have to deal with. So the first thing, as always, is to name or find and identify that longest chain carbon. So again, I always like to start and find out how many carbons are stretched across the straightaway from left to right, because sometimes that's the simplest and easiest way. So again, counting carbons, act like you're connecting the dots. You can't pick up the pencil, and once you do, you stop counting, and you cannot go backwards. So I'm just going to go left to right and number the carbons. I have carbon 1, 2, 3, 4, 5, 6, 7, 8. And let me double check there. 1, 2, 3, 4, 5, 6, 7, 8. My whole goal now is to try to get a longest continuous chain of carbons that is larger than 8. It has to be larger than 8. So I'm going to go up and to the right, and I have 1, 2, 3, 4, 5, 6, 7. Nope, not longer than 8. I'm going to go over and up. So I have 1, 2, 3, 4, 5, 6. No, not longer than 8. I'm going to go over and down. So 1, 2, 3, 4, 5, 6. Still not longer than 8. And then my last objective here, I'm going to go over and to the right. 1, 2, 3, 4, 5, 6, 7. No. So our longest chain carbon was that first one. And sometimes it's a dead giveaway left to right. But I have carbons 1, 2, 3, 4, 5, 6, 7, 8. So our longest chain carbon is going to have 8 carbons. Now, something with 8 carbons. We look on our chart that we have, and something with 8 carbons, if you look on the chart, is going to be octane. So the name of the longest chain carbon, or the parent chain, those can be used interchangeably, is going to be octane. Now we have to concentrate on numbering. Now remember, numbering is done so that the branches get the lowest possible number. So because I started left to right, I'm just going to go through how I would number it if I went left to right. So I start out here with this carbon on the left. If I started here, this would be carbon 1. This over here would be carbon 2, carbon 3, 4. Carbon 4 is our first branch. Then we'd have carbon 5, another branch, carbon 6, another branch, and then carbon 7 and 8. Now, carbon 4 was our first branch number. What we have to do, we have to think, okay, if I number it the other way, can my branch numbers be lower? So this case, I'm going to go right to left. I have carbon 1, carbon 2, carbon 3, and that's where our first branch occurs, at carbon 3. Then I'd have carbon 4, another branch comes off here, and then carbon 5, your last branch, and then carbon 6, 7, and 8. So because going right to left, our first branch occurred at carbon 3. That's the lowest possible number. So what we do here is we number the carbons. Now, I always like to put the number carbons here. It makes it easier for me to identify. So we said the lowest possible branch occurs at carbon 3, and we have to label it right to left. So we have carbon 1, 2, 3, 4, 5, 6, 7, and 8. Now, don't confuse that. That just helps us with our numbering. And so what we do is this. We always start out and we identify our branches. So the first thing that we do for a branch, and I like to box things in as I go through it. The first thing that we do for our branches, and there are multiple branches in this case, is this. At carbon 3, we always identify what is our carbon that we are dealing with. So at carbon number 3, and that's carbon number 3 off our parent chain, what we have attached is this. We have a dash CH3 group. Now, if we look up here, we are just interested in the number of carbons. So there's only one carbon in this attached group. And so if we look at this, we have the number of carbons, 1, and that is given the name of methane. So the name of this branch right here is going to become methane. Now, what we did, and what's really important, because it is a branch, we cannot have this A-N-E ending, so we chop it off, and to indicate that it's a branch, we write down YL. Now we keep moving along here. We got to name all our branches, and so the next carbon over, carbon number 4, we get this particular branch. So again, we first identify what carbon number it's at. So at carbon number 4, we have, I'm going to copy this down. We have a bonded CH2 dash CH3. Now, what's important here is in this branch at carbon number 4, there are 2 carbons. So that's the name we look up on our chart. We have 2 carbons. And so what we do here, we look on our chart, 2 carbons, that name is given as ethane. So what we do is we write down ethane as that branch name, but again, it's a branch, so we have to indicate that it has not an A and E ending, but we have to indicate that it's a branch by crossing this out and putting not A and E, but YL to say that this is an attached branch, not part of that parent chain or longest carbon chain. Now what we do, our last branch here, if we scroll over to carbon number 5, we get this particular attached group. Again, we see that at carbon number 5, of that parent chain, we get a dash CH3. Now, a dash CH3, if we looked on our chart, it's going to be the same thing that we looked up here for the carbon number 3. So this becomes methane if we look it up on our chart. But again, it is a branch, so we cannot have that A and E ending. We have to have a YL ending. So now we have to piece everything that we've done together into our name of our organic molecule. And so our name, it's going to be quite lengthy, so be prepared to go from left to right of your paper. And so our name, we always start out by naming the branch first, or in this case, our branches. So how do we decide what goes first? Well, we have to look at the name, the root name of these particular branches, what I'm underlining right now, and we have to place them in alphabetical order. So we have a methyl, we have an ethyl, and we have a methyl group again. Again, alphabetical order says ethyl is before an M for methane. And so the first group, or the first branch that we have to name, is this item in alphabetical order. And we start out by identifying what carbon number does it branch off of in that parent chain. So we have 4 dash ethyl. So we have that particular branch taken care of. And then we put, after that, because there's another branch, we put a dash mark. Now notice here we have a methyl and a methyl. Because these things are the same group, we're going to have to use a prefix. But before we can do that, we got to identify, hey, what carbon number do these things branch off of? So at carbons 3 and carbons 5, these methyl groups branch off of. And so we end up with 3, 5. And now, here comes that prefix. We have 2 prefix, which if you look in your chart, the prefix for 2 is di. So we have di to indicate 2 of these branches, and then we write the name of that branch. So we write dimethyl. Now, that identifies all the branches in this particular organic molecule. What we do on the end, after all the branches are named, what we do is we attach the name of that longest chain carbon right smack to that end of what we had just written. So we attach octane as our name. So this molecule up here that we went through this process is named as 4-ethyl 3,5-dimethyl octane. And again, if you would Google that, if you would type this into Google and you'd click on the images, you would see a molecule very, very similar to what we have here. It would have 8 carbons stretched out. It would have an ethyl group at carbon number 4, and it would have 2 methyl groups at carbons 3 and 5. So it's a long process, but it's a very step-by-step process, the very systematic way. Now what we can do, our final portion here with organic chemistry, is we can go backwards. We can start out with the name and we can draw our particular structure. And I think you'll like this a little bit more than what we have been doing. And so we want to know, we want to draw the particular structure of the branched chain alkane of 2,3-dimethyl 5-propyl decane. And so what happens here is this. We almost go backwards. And so what we do is we dissect this particular organic molecule, or this name of the organic molecule, and we do this by starting out with our longest chain carbon. Now it's always going to be here on the end, so the longest chain carbon, in this case here, I'm going to box it in. The name of longest chain carbon, I just boxed it in. It's always going to be here on the end, and so it is going to be decane. Now, if you look up the term decane on the chart that we have been referencing, the term decane means we have 10 carbons. So we write down that there are 10 carbons in this longest chain, or this parent chain. Now, what we need to do is towards the bottom, and the reason we're going to do that is because we have a attached group. Towards the bottom, I am going to draw out 10 attached carbons. So the way we do this is we literally just put carbons 1, 2, 3, 4, 5, 6, 7, 8, 9, and carbon 10. Now, give yourself a little room in between those. Give yourself some room to write some things up and down. Now what we need to do is we need to worry about our groups. And so we start out here, and we're just going to start out with left to right. So we start out here at carbon number 2. So at carbon number 2, we have in this group, we have a methyl. So right here, we have a methyl group. Now, a methyl group, what's important about this is that we have 1 carbon attached. That's what methyl means. So methyl means 1 carbon attachment. Now down here, we don't have, right now, we don't have our carbons number. So what's nice about drawing your own structure is that you can number it however way you see fit. So what we would have here is this. I just like to number from left to right, keep it simple. So again, in my purple pen here, I'm going to label this as carbon 1, carbon 2, carbon 3, carbon 4, 5, 6, 7, 8, 9, and then our last carbon is 10. Now don't confuse these. These are just markers. They don't indicate how many carbons are in that particular section. They are just identifiers or markers. And so what we have here is at carbon number 2, we have a 1 carbon connection. So at carbon number 2, what I am going to do down below here, and it does not matter if you go on top or you go on bottom, as long as you have a 1 carbon connection, we put the C there. And now notice too, I haven't put the hydrogens yet. That's going to come at the very end, but I am just putting the carbons. Now, at carbon number 3, we also have a methyl group. So again, at carbon number 3, we have a methyl group, which we just got done saying our methyl group is a 1 carbon attachment. So again, on carbon number 3, what we do is we put a 1 carbon attachment. Again, right now, don't worry about our H's. They will come later. And it does not matter if the carbon is on top or on bottom. For right now, we just want it attached to carbon number 3. So we have knocked out at carbon 2, and we've knocked out at carbon 3. There was that methyl attached group. Now we have at carbon number 5, right here, carbon number 5, we have a propyl group at carbon number 5. Now, propyl, remember we chopped off the YL ending from the A and E ending, so a propyl group is just the same thing in our chart, or the same number of carbons as a propane. So if you look in your chart here, we have propane and propane accessories here. We have propane with 3 carbons. So at carbon number 5, we have a 3 carbon attachment. And so this, I'm out of room here on the bottom, so I'm going to be forced to draw it on top. But again, it's not wrong if you draw it on bottom or top. What we get to is this. I'm going to make a 3 carbon attachment. So I have carbon 1, carbon 2, and then at top there, carbon number 3. Okay, so now we have really the skeleton of our particular structure. What we can do from here is we need to add in the hydrogens. That's the one thing that we're missing. So remember, carbon has 4 valence electrons, so that means 4 items can attach to each of our carbons. So if a covalent bond is attached to a carbon, then that counts as one of the attachments, and thus it reduces our hydrogens. So we have to have 4, no less, no more than 4 attachments. So we start out here with this carbon over here on the left. Right now it has 1 attachment. It needs 3 more attachments. So that means that this, because it needs 3 more attachments, is going to get an H3 to account for those attachments. Now this carbon at carbon number 2 has 1, 2, 3 attachments already, and so it needs 1 more, and so we do this by just adding an H. This carbon number 3, already has 1, 2, 3 attachments from our covalent bonds. It needs 1 more, so we add in the H. This carbon number 4 has 1 and 2 attachments from its covalent bonds. It needs 2 more to get to 4, and so we have H2. Carbon number 5 has 1, 2, 3 attachments already from our carbon or covalent bonds, so it only needs 1, so we just draw an H. Carbon number 6 has 1, 2 attachments. It needs 2 more to get to 4, so we have H2. Carbon number 7 has 1, 2 attachments again. It needs 2 more to get to 4. Carbon 8, same deal, has 2 attachments. It needs 2 H's to get to 4 total attachments. And same thing with number 9 and number 10 here, carbon number 10. It only has 1 attachment, so that means it needs 3 more attachments to get to 4. And so we end up with CH3. Now our last part here, we have to put the H's on our branches. And so up here, this top carbon from our propyl group has one attachment. It needs 3 more to get to 4, so this becomes CH3. This carbon right here in the middle already has 2 attachments. It needs 2 more, so that means we put 2 H's. This carbon right here has 2 attachments as well, needs 2 more, so we put an H2. And then carbon number 3, this attachment at carbon number 3, has 1. It needs 3 more attachments to get to 4, and so we end up with CH3. And then our final attachment, again, 1 attachment already, it needs 3 more, so we end up with CH3. All right, so that is what our name of 2,3-dimethyl 5-propyl decane, that's what it looks like. And again, it's a little bit time consuming to go and write the names or go and draw the structure from our particular molecule, but at the end of the day, we are able to do this through our systematic steps. All right, so I threw a lot of information at you about organic chemistry in this video. I hope you have enjoyed this thing, and as always, make sure you subscribe.